Hey everyone, Mr. Murphy here. This will be a quick one about Chapter 5.3, which is active transport. In short, active transport is all about using energy to typically move things against their concentration gradient. Things typically want to move from high to low concentration. Active transport is going to enable circumstances where the cell might want to move things against its concentration gradient in order to maintain a high concentration on one particular side of the cell membrane. And that requires energy to do because the molecules are not simply going to passively go in that direction. Instead, they need to be sort of actively pumped out. And this can happen in a couple different ways. So just to compare real quick between the other types of diffusion that we talked about, there's simple diffusion and facilitated diffusion, which both require no energy. They both rely upon the concentration gradient as the driving force. And then in the case of facilitated diffusion, it requires the help of proteins, whereas simple diffusion does not. And simple diffusion is also not specific because facilitated diffusion has a particular shape of each protein, which grabs a very particular ion or molecule in order to deliver it across the membrane. Active transport, meanwhile, is also going to have that specificity because it's mediated by proteins, but it does require energy, and that's what is listed here, ATP hydrolysis. Hydrolysis, remember, is the breaking off of a piece of a molecule through the addition of an OH on one side and H on the other side. In the case of ATP, what that means is the breaking off of that third phosphate. So ATP becoming ADP, adenosine diphosphate. So that's when you see that word associated with ATP, that's what it's referring to, and it's the opposite of ATP phosphorylation, which would be, or actually be ADP phosphorylation, which is the adding of the phosphate group. So we'll get into that a lot more when we get to energy, but just to familiarize you when you see those terms. So the source of this energy, as just discussed, is most often ATP, and that's an example of primary active transport. It's very directional. It moves that substance against its concentration gradient. Now, depending on the circumstances of the cell, active transport, because of its specificity, might by chance be moving something with its concentration gradient, but the existence of that mechanism is there to counter the concentration gradient. I suppose what I'm saying is that the cell is a dynamic and crazy place, and sometimes shifting amounts of things means that maybe we're in an atypical situation. But active transport is always going to be moving something in a singular direction, which is most often against its concentration gradient. The two types are primary and secondary. So primary is actually using the ATP for energy in order to achieve this. Secondary is also a type of active transport, but it doesn't use ATP directly. Instead, it's using some other energy resource within the cell, such as the concentration gradient of another molecule. So, for instance, in certain cell types, there are what are called symporters or antiporters. It just depends on what direction they're moving something, where maybe there's a high concentration of sodium outside of the cell and a low concentration inside. So you can have a protein that's allowing the sodium to move into the cell. However, it's possible to capitalize upon that movement and allow the energy of the moving sodium ions into the cell to simultaneously basically sneak something else into the cell as well. And that would be the case of what's called a symporter, that it's moving in the same direction into the cell. You could also have the circumstance where maybe the movement of the sodium in is allowing something else against its concentration gradient to get out of the cell. That would be called an antiporter. But the point is that we can capitalize upon other chemical situations inside of the cell to get the energy necessary to move things against their concentration gradient, which again is a hallmark of all forms of active transport, moving against the concentration gradient. So the sodium-potassium pump is a prevalent example. This is a mechanism by which the cell is maintaining concentrations of both sodium and potassium against their concentration gradients, both within and outside of the cell. And it does this by using a molecule of ATP to move 2 potassium and 3 sodium ions. And here's an example of this, where the sodium-potassium pump here experiences a shape change because of the hydrolyzing of ATP. So this phosphate group breaks off, which changes the shape of the protein. So if we take this step by step, here's the pump. inactive. It's got 3 sodium sort of locked and loaded, but nothing's happening. And ATP comes and binds. When the ATP hydrolyzes and breaks off that phosphate group, because of that little chemical interaction here, it changes the shape of this protein, which then sends the sodium ions out and allows for potassium ions to then bind. And then when the sodium ions have left, the potassium is locked and loaded. The potassium ions then move in, and when that phosphate group is liberated here and allowed to leave from the protein, the potassium can sneak into the cell. And you'll notice by looking at the little circles and squares here that we're actually moving these things towards high concentrations in both cases. The sodium is high on the outside. It doesn't want to passively leave the cell, but this pump is actively pushing more sodium out against its concentration gradient, while at the same time moving potassium in against its concentration gradient. But it can do that because of the energy and the shape change provided by ATP. So secondary transport, just to reiterate, is using energy that's basically being regained by letting ions move against their concentration gradient move across the membrane with their concentration gradient. So for instance, now that I have this huge sodium concentration on the outside, I could have another protein that's allowing sodium to sneak in, but while doing that, it's allowing something else to move in as well, and that something else might be moving against its concentration gradient. So it's still active transport because it ultimately is using energy from some source. In fact, the energy used in that example would be ultimately ATP at the sodium-potassium pump, which is creating that difference in sodium concentration. So it's just like layers of the same thing. It's just, are we directly using energy from ATP, or are we sort of indirectly using the energy from ATP, several steps later? That is active transport, both primary and secondary. If you have questions, let me know.